Olá a todos, meu nome é Hélio Dias, presidente do IVPESP, que é o Instituto para a Valorização da Educação e da Pesquisa no Estado de São Paulo. Somos uma entidade de direito privado, sem fins lucrativos, e nosso objetivo é se tornar uma ponte entre a sociedade e o conhecimento. Contamos com membros representativos da sociedade científica, empresarial e universitária. Contamos com um centro de inteligência e especialidades multi-institucional e multidisciplinar, com membros do Brasil e de outros países. Em nosso portal, vocês vão encontrar as nossas principais ações até o momento, que são workshops, encontros temáticos, feiras e informações de interesse da sociedade na área da divulgação científica. Nosso principal objetivo é tornar o conhecimento acessível a todos e contribuir para o aperfeiçoamento das instituições. O IVPESP conta com um certificado de regularidade cadastral de entidades do Estado de São Paulo, o que nos credencia para parcerias com entidades públicas e privadas. Você vai assistir agora a mais um evento organizado pelo IVPESP. Obrigado e boa palestra a todos.
Bom dia. My name is Wolfgang Bauer, and I'm very pleased and honored to be invited to this workshop. And the title of my talk is Energy for the 21st Century World Economy, Problems and Opportunities. Let me start with the problems. In a 2010 poll by the British Broadcasting Corporation World Service, people from 22 countries, over 25,000 people from 22 countries were asked what they consider to be the biggest problems in the world. And you can see the list ordered by the most number of responses, which starts with extreme poverty, environmental pollution, rising cost of food and energy, and so on. The ones I've highlighted in red can be directly traced to use and procurement of energy resources, including war or armed conflict, where I would like to add that most wars or armed conflicts in the 20th century were fought over access to fossil energy resources. This slide from our 2013 textbook shows the world's power consumption. The vertical axis is shown in units of terawatt, in units of 10 to the 12th watt, and it's the average power consumed by the entire world population as a function of the calendar year, which is shown on the horizontal axis. And there are two features that are absolutely jumping at you right away. One is that the world power consumption rises very steadily from a little over 7 terawatt in 1970 to just about 16 terawatts right now. And the second feature is that when you split the power produced up between the different production sources, fossil in red, nuclear in green, hydroelectric in orange, and all alternative resources in blue, you can clearly see that the vast majority of the power produced around the world is produced as a result of using and burning fossil fuel. As I said, currently we use 16 terawatt. It's increasing strongly with time. It's overwhelmingly satisfied with fossil fuels. And you may say, well, this is the biggest problem facing the world. But I tend to be more optimistic in my outlooks, and so I would call this the biggest opportunity in our lifetime. And I will explain subsequently why I come to this conclusion. Typically, when I give presentations, I find that it's counterproductive to use equations in my physics talks. but some equations are essential, and so I'm going to give you the most important equation of my presentation right away, and it is energy is equal money. And this holds for every currency, if it's euro or Japanese yen or Chinese yuan or British pound or US dollars or Brazilian reais. And I can show you an impressive example for this. So what I plot here, horizontal, is the gross domestic product per person per year. So the average income of a person in a given country per year in US dollars. On the vertical axis, I plot the energy use per person per year in gigajoule. And what you can see is that all these countries that I plot here lie basically in a narrow band. And the blue cross that I show now is actually the world average. Obviously, the road to prosperity is the road to increase of energy use. And in order for the developing countries and the BRIC countries to reach the standard of living enjoyed, for example, in the United States, global energy consumption has to increase very, very drastically above what it is right now. In the US, typically the energy consumption is between 300 and 350 gigajoules per year, and I just want to illustrate what that means. So 350 gigajoules per year, the average power consumed by each individual human being in the United States is then something like 11 kilowatt. You can compare this to our bodies. A typical modern diet is about 2,500 calories per day, which is about 10 megajoules per day. So the food consumption per year is about 3.5 gigajoules or 1 megawatt hour. That means the 350 gigajoules that the average citizen in the US consumes about now is roughly equivalent to the food consumption of 100 people. Steve Chu, before he became the Energy Secretary of the US, when he gave public talks on this fact, he called these 350 gigajoules that the average US citizen consumes per year, quote, the equivalent of having about 100 energy servants. This graph shows the world's oil consumption split up for different countries. At the very top is the United States, followed by Europe, and all other countries are a significant factor below, but you can see that China is now rising exponentially in its oil consumptions and is projected to surpass Europe and the United States in the next 10 years. Brazil also has an exponential rise, as highlighted here, but the rise slope is much, much smaller. The problem is that globally we will be running out of oil. And this can be best illustrated on this graph, which I borrowed from Steve Koonin when he was chief scientist at British Petroleum. He showed this at Michigan State University, based on data from EIA, the Energy Information Agency of the US Department of Energy. And you can see in black the data that summed up the known history until 2000, and then shown are extrapolations for low, mean, and high expected recovery. And you can see that the peak oil recovery will be reached somewhere between 2026 and 2047, and then it will rapidly decline. And so since we are here in time, you can see 50 and 100 years from now, we will really not have oil at our disposal anymore. Already you can see that drilling for oil gets more expensive and more dangerous, and nothing illustrates this better than the Deepwater Horizon oil rig explosion and subsequent environmental catastrophe in the Gulf of Mexico from 2011. So where do all these fossil fuels go when they get burned? And the main answer is actually they get released into the atmosphere. So let me talk a little bit about our atmosphere to start this out. The composition of our atmosphere is overwhelmingly nitrogen, 78.08%, and oxygen, 20.95%. And then there are trace gases. Leading is argon of almost 1%, 0.93. And then for the purpose of this presentation, most importantly, carbon dioxide at 0.04%, 400 parts per million. The total mass of the atmosphere is easily calculated and is 5.2 times 10 to the 18th kilogram. And so from that information, we can then easily infer that 1 ppm by volume of CO2 in the atmosphere corresponds to 7.9 times 10 to the 9 tons. So about 8 billion metric tons of CO2 is 1 part per million. So what is the record of CO2 in the atmosphere? And we actually have fantastically great data reaching back all the way to about 500,000 years before our time. And these are extracted mainly from ice core drills in the Antarctic and in Greenland. And in this figure, which we produced for our textbook in 2013, all of these data are summarized. And what you can see in purple is the Vostok ice core data. And the most striking feature of these is they go up and down, and they always lie between 190 and 300 parts per million. And then at the very, very right edge of the graph, near zero and slightly above zero, are all the other data that reach all the way up. And these are superpositions of ice core data, of South Polar air data, of Mauna Loa, which is a volcano, an extinct volcano in Hawaii, air data, and so on. And so let me just zoom in on the last 1,000 years. And then this is what you see. You see a basically horizontal progression of data points since the year 1000 after Christ until about 1800 or 1850, when you can observe an almost exponential rise caused by the onset of the Industrial Revolution and subsequent strongly increasing burning of fossil fuels in all industrialized nations. And I zoom in further just for the last dozen years or so, and you can see oscillations in the CO2 concentration in air. The green data are the Mauna Loa data from Hawaii, and the red or orange data are South Polar air data. You can see that they oscillate in annual cycles, which correspond to the growing and decay of the plant mass in each hemisphere. And you can see that the South Polar and the Mauna Loa data have opposite phased oscillations because of the opposite cycle of seasons in the northern and southern hemisphere. So the latest readings, I just looked that up a couple of days ago. On May 11th, it was 401 ppm. It will dip for the next 2 or 3 years below 400 ppm again in some parts of the time, but then it will move towards 500 ppm. Along with the carbon dioxide, we put more and more air pollutants in the air. So this is a study that just came out last November, and the basic upshot is that 200,000 early deaths are caused by these micropollutants, 2.5 micrometer or less. Global temperatures
are rising as a consequence. The scope of global temperature is a number that's not so easy to obtain because you have to average over time and over space. Here you can see a snapshot just from 1 month in 1992 from satellite data. You can see that the temperatures are all over the place depending on where on Earth you are, but you have to average for each square kilometer the temperature to get some global temperature as a function of time, and then you average that over the entire year. And all this is plotted here for years since 1880 to now. And you can see this is the average temperature during the 20th century. You can clearly see that there's a strong rise, linear rise. Some people claim that it has stopped here because during the last 15 years or so, we've reached a maximum. But clearly you can see, there's fluctuations in here, and the tendency is very, very obvious. And the tendency is that the temperature rises about 0.2 degrees per decade. Incidentally, whenever I give a global warming talk around the world, inexplicably it just turns cold for a while. So that ice storm yesterday in São Paulo, that was clearly my fault. Now, the predictions are that it will get hotter and hotter. So this is just shown for the US in this report. So this is the current distribution of the number of days above 100 degrees Fahrenheit, which is body temperature, so it's 38 degrees Celsius. And you can see the desert in Nevada and California and Arizona has lots of these days. The rest of the country, only very, very few, about 10. And depending on how much you think that carbon dioxide emission will rise, you can see that for the high emission scenario, by the end of this century, you will have Texas, for example, will have 1/3 of the year, every day it will reach above body temperature. Sea level will rise. This has received very recent press because of the West Antarctic ice shield that seems to be in decline in a way that's irreversible. You can see these bigger and bigger pieces breaking off. Now, for all the ice that swims on top of the water, that's not a problem, but for the ice that's supported by rock below, that is a huge problem. If all the ice in Greenland would melt, then the sea level would rise by about 7 meters. If the entire Antarctic would melt, then it would be 70 meters or so. If the entire North Pole melts, then you get no sea level rise because the North Pole is not supported by land mass below it. And here are the data of sea level rise, and in this paper, Vermeer and Ramsdorff fitted this to this differential equation and see where it took them. And by the end of this century, the global sea level will be, a meter and a half higher than it is right now. It doesn't sound like such a big deal, 1 meter, but all the weather events that are usually happening are superimposed on the sea level rise, and so large-scale weather events like this Hurricane Sandy here that hit the U.S. last year and that influenced large portions of New York City, all these weather events get amplified by sea level rise. The U.S. Navy has its largest base in Virginia, and I was at a meeting just this past December where the U.S. Navy now is thinking about giving up this naval base because of sea level rise. And when the U.S. Navy does these things, you know that there's a scientific factor because they wouldn't give up a multi-billion-dollar base for nothing. The oceans will get more acidic. For the oceans, we also have data from the last 500,000 years or so, and you can see that pH level is always in a very small band, but it has been falling lately, and the prediction by the end of the century is that the pH level will be reaching 7.8, so it will be a lot more acidic than right now. Coral reefs will suffer, fish populations will suffer. The only thing that seems to be thriving in more and more acidic water are jellyfish. So that looks bad, but I'll show you something that could look even a lot worse. So what I plot here is the data that I have already shown you in blue, which is the carbon dioxide content. Actually, this is just taken from the ice in the South Pole. And I've told you it's between 190 and maybe once it touched 300 ppm there. So this is the scale for the CO2. Now, what is also measured there is the temperature in the air above the ice. So for the last 500,000 years, these two graphs have been tracking each other very, very closely. And I'll just superimpose it better by shifting them up. And you can see there's a very, very good correlation between the two. Now, you can argue that sometimes or often the temperature falls first and then the carbon dioxide level trails. And so some politicians have used this argument to say it's actually the temperature that causes the carbon dioxide, not the other way around. But in the last century, we have shifted all this out of its equilibrium. And now I'll plot up there where we are right now. And so obviously this is a tightly coupled system. Obviously we don't know exactly how it will react, but if it responds linearly, then the global temperature should not just rise by 1 degree or so as it has over the last century, but it should rise by 13 degrees. And you can just speculate how livable São Paulo would be if the temperature is 13 degrees higher every day on average. So that, I think, is the biggest problem. So with the greenhouse gases, I have to admit that many of these feedback loops in the atmosphere are poorly understood. Most climate models, and all that I know, cannot predict, for example, the monsoon season in India, which is a big deal if you live in the Indian subcontinent. So it's not at all assured how Earth's climate will respond with the increase in temperature that we see in the CO2 level that we have produced. So it could be that Earth's climate would respond fairly linearly. It could be that the Earth's climate just counterbalances this. We don't know, but there also may be a runaway solution, sort of like what has happened on Venus. And so I'm not a chemist, but if I was a chemist, the number one motto that I would have for chemistry experiments: don't do the experiment if you are the one sitting in the petri dish. And so this is an experiment that we're presently doing that we really should not do. Of course, yesterday's ice storm is this question: how do you explain that, right? And that has been sort of worldwide throughout history. The response for all doubters, this guy doubts that the Earth is round because you can hold his ruler down; it's pretty flat. And this guy in the 17th century doubts that gravity exists because hey, there's a bird out there. Doesn't fall down. Evolution, this discussion is still going on in the US. And global warming, this is the present discussion. So what do we do with the CO2? How could we get rid of the CO2? And one idea is actually capture the CO2 at the production process and then put it away. And I have worked as a consultant for an oil company, British Petroleum, and we looked at this. And so we studied the feasibility of doing this, and I just want to give you a numerical example how hard this is. So let's say we really had the will and the money to do this, to capture all the CO2 that humans produce in just 1 year, and we could pressurize it and liquefy it, and so then we can make liquid CO2, and we can store it in tank cars like this, and just fill it into a train. And each of these tank cars holds 131,000 liters. And the question is, how long does this train have to be to store 1 year's worth of output? Just think about this. 10 kilometers, 100, 1,000 kilometers. Well, this train actually would go 65 times around the Earth's equator. It would be 2.7 million kilometers long. That shows you how impossible it is to stop CO2 enrichment of the atmosphere if we want to insist on burning fossil fuels. So that's the end of my problem section. Now here for the opportunity section. So renewable energies. For each one of these I can give a 1 hour talk and a half, but I don't have the time today. So hydro dams, ocean currents, surface waves, wind, solar, geothermal, deep geothermal, where you drill to about 6 kilometer depths where the rock is hotter than the boiling temperature of water, and biomass. But I just want to focus on biomass, talk a little bit about bioethanol, and then mainly about biogas. So here's a graph of annual bioethanol production in just 2 countries, Brazil and the US. Those are the 2 leading countries in bioethanol production. So Brazil historically was ahead of the USA until about 2007, when the US really started to subsidize bioethanol production from corn. This gentleman, David Pimentel, and his colleague Ted Patzek, they looked into life cycle analysis of bioethanol production from corn, and what they found was actually shocking. They counted how much fossil fuel energy you have to put into bioethanol production and compared it to the energy that you get out in renewable energy. And what they found was that it takes 29% more fossil fuel energy for bioethanol production from corn than what you put in. So this is actually a way to bankrupt yourself very, very quickly. Now there are other numbers that actually make this a positive exercise, but not very positive. They also looked at switchgrass and at wood, and the numbers are worse. Looked at biodiesel from soybeans and sunflowers, and they're also negative. So I'll just give this as a warning. If you don't do this right, you're actually putting more fossil fuel into the production process than what you get out in the end. So in the US, there is a huge effort to not just use the sugars in the corn, but also the cellulosic material to make bioethanol. Now, this can be done, as this little termite shows, because in the hindgut of the termite, there are actually microbes that are able to break down the lignin in the wood. That's why termites can eat your house when it's built out of wood. So that technology has been around for about 300 million years on Earth, but we have just not been able to capture it. And so British Petroleum gave $500 million to the University of Berkeley, Lawrence Berkeley National Lab, University of Illinois, to do exactly this. The US Department of Energy gave $125 million to us at Michigan State and to the University of Wisconsin. But so far, it has not worked. I just gave a similar talk that I give today here at the University of California in Berkeley, and the director of this effort here, Energy Biosciences Energy Institute, Chris Somerville, told me that he is slowly ready to step away from this idea that this would work. They have worked on this for 7 years now, spent about $350 million, and they're not successful. So let me show you something that is successful. And this is this biogas power plant. So the basic operation is very simple. We grow corn. This is an effort from my home country in Germany, and I'm actually co-owner of this biogas power plant. I will show you pictures from 6 different biogas plants that we have. So we grow corn. We would love to grow sugarcane, but it doesn't grow in Germany. Sugarcane would be better, so we have to grow corn. Corn, when it grows, takes groundwater and sunshine and atmospheric carbon dioxide and translates that into the biomass, the green stuff that you see here. And then what we do is we shred the corn at harvest time, the entire plant, not just the cob. and throw it in the silo. These type of harvesters are used. I'm sitting there behind the glass and film. This is a very violent process, and it just shreds the entire plant, loads it on these trailers, and you know, it's transported to some big mountain where you just push it all on top of this and drive over it with a tractor to eliminate the air out of it. And then it actually stays in the silo and is usable the entire year round. So this is one of those silos, and for each of our power plants, we take about 25 tons of the shredded corn silage per day and add 11 tons of cow dung to it. And we mix it, so here's a silo in the background. This is this tractor that just dumps it in here into this mixer. This rotating drum pulls it in, and it pulls it into a fermenter. And this is a picture of my brother looking down into the fermenter, and I just held my iPhone there and showed what he can see. And this is the kind of mass that is in there. Oxygen is kept away from it. And so these microbes are basically the same microbes that act in a cow's stomach. And cows produce lots of methane, and due to these microbes, all this bubbling that you see is that. We constantly stir this so that the microbes have maximum contact with new feed material, and we capture this methane. That's the entire thing. We add some fermentation chemicals that accelerate this process, but it's basically the same as a giant cow's dung. Once all the gas is removed from this, we have 10,000 cubic yards or so of a fertilizer mixture, which is solid liquid. It's high quality. We just spread that back on the fields, and we don't use any artificial fertilizer, and have not for the last 7 years. And in the end, there's no soil deterioration. For most of these agricultural processes, artificial fertilizer is the most energy-intensive additive that you have to add to the life cycle, and we don't have to do that. We store the gas in these big secondary fermentation silos. We harvest about 7,000 cubic yards of biogas per day, and biogas is 60% methane and 40% CO2. And this is actually flammable, and we can just burn it in combustion engines. And they sit in these containers, they're soundproof, and so these engines drive generators. The overall process is 82% efficient. 82% of the primary energy in the biogas is converted either into electricity or heat. So 40% goes into electricity with these 700 horsepower engines, and another 42% go into heat, which we can use for several purposes. So the bottom line of this is it costs about $3 to $5 million US to build this, so it's about 6 to 8 million Brazilian reais. The land required to grow this biomass is about 150 hectares. It produces 6.2 million kilowatt hours of electricity and another 6.5 million kilowatt hours of thermal energy. Typically, when I compare renewable energy forms to each other, I always use 10 cents per kilowatt hour as a price point. This may not be realistic, it may be higher here, or if you get electricity from hydropower, it may be lower, I don't know, but 10 cents per kilowatt hour is just my normal comparison figure. In the US, certainly it's much higher in residential areas, but if you use 10 cents per kilowatt hour, this whole initial investment pays off in 3 to 4 years. So here's the energy balance, all the energy life cycle integrated that we put in and that we get out. So the input is listed here, and these numbers are always in megawatt hours. So the three large components are the diesel that we burn in the tractors when we plant the corn, when we put on the herbicides, when we harvest it, when we transport it. All of that together costs 176 megawatt hours. We add these fermentation additives. The exact composition, I don't know. It's a trade secret of the company that that we have a deal with. But these enzymes, they have to produce them at some kind of profit. And so I just calculate the overall energy that they give us from the price that we pay for it, and pretend that it's all diesel fuel. And so if that company makes any kind of profit, my number is actually a high estimation. So this should be considered an upper limit, and then it's 171 megawatt hours. Farm equipment does not last forever, it depreciates over time, and so this depreciation is folded in here over a 10-year life cycle of these tractors and plows and so on, and that costs you 180 megawatt hours. And then corn seed, we have to plant the corn seed each year new, that's 92 megawatt hours, herbicides 95. So this is the overall. The electricity output is shown here. The entire height is the electricity that we get, and then this transparent piece, we have to use this electricity as part of operating the power plant. You know, the steering mechanism, conveyor belts, valves, computer controls, all this costs electricity, and so that's the part that we use ourselves. So the net output is only the solid fuel. And this is the heat output, which is slightly bigger. We also use some of the heat to keep the fermenter always at body temperature when the microbes operate best. We can use the extra heat to do some other useful things with. So one of our plants is actually, this is our entire plant, this is the silo. So this plant is here. And next to it are all these very, very large greenhouses. And what we actually do is we deliver heat for the greenhouses in Germany. This is in southern Germany, near Munich. In the winter it gets really cold, below freezing, and so the greenhouses help, but you have to also supply some additional heat for the plants so that they can grow. And we do this only from this little power plant here. So 6 million kilowatt hours of heat can flow into these greenhouses. And we actually give them also a slight enrichment of the CO2 in their atmosphere, because plants really like a 1% atmosphere of CO2. So we enrich it about 20 times higher than the ambient air. And the result is that in these greenhouses they can produce the earliest strawberries in Germany. So, and this is a very desirable product in Germany, so we can make lots of money with it. So the biggest factor that we need to talk about is the net energy ratio. And the net energy ratio, as I said, is the total energy output of your renewable energy operation divided by the fossil energy input integrated over the life cycle. And so here's from 0 to, well, some high number. And I plot a horizontal line at 1 because you need to be above 1 to have any chance to do something for the planet and also to make this economically profitable without artificial subsidies. So the paper that I already showed you by Pimentel and Patzek is listed here at 0.79, so this is a disaster. There are other industry estimates, and this is a very comprehensive recent study by Liska et al. From the University of Nebraska, and they have looked at many bioethanol power plants from corn, and they found ratios between 1.2 and 2.2, with the majority of them concentrated all around 1.5 or 1.6. So at least this is net energy larger than 1, and so this is a positive result. There is another study out of Argonne National Lab that was just published in 2012, and their number agrees with Liska's number, and it's about 1.6 for bioethanol produced from corn. This is still not a very good result. They also looked at other ways to make bioethanol, sugarcane, and I'm sure Professor Goldenberg will talk more about this. This is 4.5, so this is very good, 3 times better than corn. Slightly better is switchgrass and miscanthus, because these two plants don't have to be planted each year and they don't have to be fertilized. So they are advantageous, at least in this study. And so now I will show you how our number for corn to biogas compares to all of these numbers. and it's actually just about 8 or 7.9. And I've just published this at the end of last year in this journal, and the recommendation would immediately be stop all of the bioethanol production from corn and instead go to biogas, and you're producing a lot more renewable energy. So the energy efficiency of the overall process, we say that the solar constant is 1,400 watt per square meter, but what really arrives at ground level in Germany is only 170 watts, not 1.4 kilowatts. That's the angle of the sun, day and night, clouds, seasons, and so on. So the 150 hectares that we use for each of these plants, the maximum power capture then is 250 megawatts. The present efficiency is the 0.7 megawatts per plant that I said earlier, divided by this number, is only 0.3%. So there's clearly room for improvement, even though this is a typical number for photosynthesis. So we can do research, and we're in the process of this, on better microbes, better energy crops, better conversion processes. But in addition, if one does this in Brazil, you have two different advantages. First, your cosine theta, a lot closer to the equator, on the equator if you want, than Germany. And then there's also a much longer growing season here. In Germany, the growing season starts just about now in May. In the end of September, you already have to harvest the corn. The rest of the year, there's no plant growth. So here you can see a map of the global sunshine yield, so to say. And Germany is up there. Brazil obviously is down here, much better. Germany is a very cold and dark country in comparison. So this would work much better here than it does in Germany. So transportation fuel. If we were to use our 150 hectares, then we could make 680,000 liters of methanol, of bioethanol, out of this corn yield. But we are producing 2.6 million liters of methane per year. So this is a factor of 3.8 higher. And it turns out that the heat of combustion of methane and of ethanol are just about the same per liter. It's about 2/3 of gasoline. And I have actually rented a car here in Brazil that was running on methane as a secondary fuel. Just switch. So this technology of conversion is already there and can be done. So for each hectare, for comparison, if we were to produce bioethanol, we could drive the Chevy Volt 5,000 kilometers. If we would capture the methane from the biogas process that I'm talking about and liquefy it, we could drive it 19,000 kilometers. But the Chevy Volt also has an electric engine, so if we just capture the electricity in the process that I discussed, we can actually drive the same car 23,000 kilometers. So this is a rather dim picture, but this is Arun Majumdar, who was the founding director of this US Department of Energy ARPA-E project for advanced energy projects. And in this talk, he says, well, they get 80 gigajoules per hectare, and their dream, their long-term dream would be to double that to 160 gigajoules. So if I look at our plant and then I look at the energy yield, I'm already at 150 gigajoules per hectare per year right now, and that's only electricity. And if you add the heat to it, you come up with about 300 to 350 gigajoules, which is a factor of 2 better than what he claims is the long-term dream of the bioethanol production from corn in the US. So what I'm saying here, this is a famous Scientific American article that I recommend highly. It's from 2006 by Sokolov and collaborators, and they say, well, to get fossil fuels out of our lives, you have to do all kinds of things. And they have this famous wheel of wedges, and 15 different things are needed, and one of these wedges is drive 2 billion cars on ethanol using about 1/6 of the world's cropland. So if we do ethanol, if we do biogas instead, so methane, then we can reduce this to 1/20th of the cropland, and that's much better. In the US, currently we're producing about 50 billion liters of ethanol, and if we convert just this US corn yield to biogas reactors, we could make 190 billion liters of methane. That's roughly a $100 billion per year profit that we get from this. One more point, greenhouse gases. It's a useful number to know that, so this is the number of grams of CO2 produced in power production per kilowatt. For coal, it's almost 1 kilogram of CO2 that you produce for each kilowatt. For wood, it's slightly better. Gasoline, slightly better yet, so it's less than 600 grams. For methane, it's about 1 pound of CO2. So a factor of 2 better than coal, and that's why it's advisable to switch off all coal-fired power plants and run them on gas, and already doing a lot of good. So how does our technology compare to this? So this is our net CO2 emissions, which basically comes from the diesel fuel that we burn in the tractors and all the other elements that I discussed in my life cycle analysis. So it's 25 times cleaner than burning methane. But in addition, remember I said we add this cow dung. And cow dung, if you just see what farmers do with the cow dung, they spread it on the field because it's a good fertilizer, but it contains a lot of methane. And so methane is 25 times to 50 times more powerful as a greenhouse gas than CO2. And we prevent this methane from this cow dung to escape into the atmosphere. So for each ton of methane that I capture from the cow dung, I credit myself 25 tons of CO2. And that then gets me the net efficiency of the power plant, and it's right here. So it's a mitigation of over 200 grams of CO2 per kilowatt hour that I produce. There's fairly large error bars on that depend on, among other things, the storage time of the cow dung before it goes into our process or before it would go in the field. At Michigan State University, we just built and finished a new anaerobic digester that uses no energy crops at all. It uses instead food from our cafeteria system, so all the food that's prepared and not eaten, all the stuff that's cut off from the food before it's served, and all the remainder that are scrapes off the plates are collected in these yellow tons and then added to the fermenter. In addition, we use substrate from our wastewater treatment plant and from our farms. And so we make electricity or transportation fuel and heat from this. This is only a very small scale operation, about 500 kilowatt or so. In the future, we also want to use a technology that's employed here at this large scale farm in Indiana, where you can clean the biogas and turn it into transportation fuel, as I have already discussed. So one recommendation for Brazil that one could look at, I don't necessarily want to recommend, like I recommend for the US, to switch off all bioethanol production. But the bagasse, that is the leftover from sugar production or bioethanol production, is very valuable in energy content. And one could shred it and add it to biogas reactors of the kinds that I discussed. Instead, currently, it's simply burned. And yes, this is also energy, but you can already see lots of micropollutants come out of the smokestacks. And this incinerator operation is less than half as efficient as this biogas reactor that I discussed. So fermenting the bagasse in a bioreactor to produce biogas will result in a much higher net energy ratio and therefore much higher profits. So this is my summary. Human-generated CO2 from the burning of fossil fuels has finally managed to have a measurable and noticeable effect on the global climate. This global warming is real and man-made, notwithstanding what happened in the local weather in Sao Paulo in the last week. The consequences are sea level rise, ocean acidification, and increased air pollution. We cannot seriously suggest to just reduce our energy consumption because that would lead to widespread poverty. So in order to preserve and increase our prosperity, we need to move to renewable energies. One can discuss all kinds of renewable energies. The small segment that I focused on today is biogas production. And I would claim that it is preferable form of converting biomass and electricity into our transportation fuel. And I thank you for your attention.